All right, this is the second half of topic number 3 for today's lecture, which is Monday, April 10th, where we're discussing applications and looking at examples of stoichiometry for reactions that occur in solution or aqueous reactions. Here we are looking at the precipitation reaction that occurs when we mix silver nitrate and strontium hydroxide. We found through our double displacement and net and complete ionic equation analysis that our net ionic equation says that it takes 2 moles of silver ion to react with 2 moles of hydroxide ion to form 2 moles of our solid insoluble product or precipitate, which was silver hydroxide. So now we have answered, right, part 1 of this question. Is a precipitate formed? Yes, a precipitate is formed. And the next part of our question is, if so, how much is formed in grams? So in order to answer this question of how much, which is inherently a quantitative question, right? How much quantity is there present? We need to undergo our stoichiometric analysis. We need to do our stoichiometry calculations, meaning we need our ratio. So that's why we worried about getting our net ionic equation in the first place. And we also need to know what's in our pantry, or what we actually reacted, the mole quantities used in lab for real when this reaction occurred. So I'm going to take this information and I'm going to just jot it down beneath each of my reactants here, just so kind of as a reminder. So I had 0.200 molar AgNO3, and you know what? Just so that we're familiar with it and get practice with it, I'm going to rewrite this using our bracket notation. So the concentration of silver nitrate is 0.200 molar. And then the quantity that we reacted was 35.2 milliliters of that solution. And then for our hydroxide, let's see here, that all came from our strontium hydroxide. So this was 15.4 mils of a 1.25 molar solution, strontium hydroxide. So concentration SrOH2 is 1.25 molar. And we added 15.4. Yes, 15.4 milliliters. Now, before we can go on and try to get moles, because that's what we need, right? These are mole ratios. So in pink, we are given from our recipe the mole ratios. And from this information, I need to get my mole quantities. I need to be very particular and specific about the mole quantities that I need, meaning mole quantities of what? So based on our recipe, our net ionic equation, I need the moles of silver ion and I need the moles of hydroxide ion. So let's just kind of think about the dissociation that occurs when you dissolve, let's say, silver nitrate in solution and strontium hydroxide. So silver nitrate, that is everything in a 1-to-1 ratio. So 1 unit of AgNO3 dissolves into 1 unit of silver and 1 unit of nitrate. So this means that the concentration of nitrate ion, not nitrate, we don't care about that, the concentration of silver ion is equal to the original concentration of silver nitrate. the whole solute. Okay, what about for our strontium hydroxide? So if I were to think about what's going on in solution here, I got to pay attention to what's happening with my subscripts in my chemical formula. So if I were to look at strontium hydroxide, SrOH2, when I dissolve 1 unit of strontium hydroxide into solution, I create 1 strontium 2 plus ion, but also 2 hydroxide ions, meaning that my concentration of hydroxide is equal to twice that of the concentration of the overall strontium hydroxide solute. Because for every 1 unit of solute dissolved, I generate 2 units of the ion that I care about or that's directly involved in the formation of our product. So now that I know this, I can kind of reframe this. I know that my concentration of silver is still going to be 0.200 molar. And now I know that my strontium hydroxide is going to give me a hydroxide concentration that is twice that of my 1.25 molar. So that is what, 2.5? Yeah, math. Okay, so we've got that concentration of hydroxide is 2.5 molar. Okay. Now, do I still have my mole quantities? Like, do I have a number of moles of silver reacted and a number of moles of hydroxide ion reacted? No, I do not. So let's go ahead and get our mole quantities of our silver reactant and our hydroxide reactant. Meaning, let's look in our pantry. Let's see what we have available to react. All right, remember, molarity, moles per liter. Since I have to say the word per in that unit, that's a compound unit, so that's always going to be my conversion factor. Meaning that my starting point is going to be my lab measured volumes of each solution. So I have for silver 35.2 milliliters of my silver ion solution. And for my hydroxide, I have, let's keep it in terms of our solute. No, let's keep in terms of ions. That make more sense. We're doing net ionic equation. Let's keep it in terms of ions. So hydroxide, that was 15.4 milliliters of a solution containing hydroxide ions. And remember, molarity is moles per liter. So if I want any of these volumes to be expressed in terms of liters, then I need to move my decimal over 3 places to the left, or I can write this as times 10 to the negative 3 liters Ag plus. Again, chems are cheap and lazy, so why don't I slap on my 1,000 times smaller scientific notation so that I'm put into liters. And it should be smaller because I have very, very large amounts of milliliters that can fit into a liter. So if I have some quantity of milliliters, it should be a fractional amount of liters. All right, now this is where our concentration is going to come in handy. This is what's going to put us into the mole quantities of each thing that we need. So I know, based on my analysis of what I had in my pantry, or at least pieces of information about what I've got in my pantry, I know that for every 1 liter of my silver solution, there are 0.200 moles. That is simply my concentration of my solution of silver ions. Okay, let's do the same thing for our hydroxide. And let's not forget that we did this analysis of how strontium hydroxide dissociates so that we could get the concentration of just hydroxide ion, because that's the only thing that we need according to our recipe. Strontium was a spectator ion. All right. So there are 2.50 moles of hydroxide ion per 1 liter of our hydroxide solution. Okay, so now we have to do some math. Probably have our calculators ready. If you want to pause and grab your calculator, I highly recommend it. So that's 0.352, that's our volume of silver, times 0.2. This is all a product, so we need to have this in scientific notation. So this is 0.0704 moles of silver ion. So I finally have my number of moles of silver ion. I'll rewrite this. And now let's do our hydroxide solution. Wait a minute, am I off by a factor of 100 or 10? I think I am. So 0.0352 times 0.2. Yeah, okay, so this is 7.04 times 10 to the negative 3 moles of silver. Okay, now I've also got here for my strontium, that's 0.0154 liters of hydroxide solution times my 2.5 molarity gives me 0.0385 moles of hydroxide ion. And now what I'm going to do is I'm just going to rewrite my recipe, which is my net ionic equation, and then include underneath that what I fully know about my pantry, meaning what I have available to react, because once I've got 2 different reactants reacting in 2 different quantities, meaning looking through my pantry and I find different amounts of things like butter and vanilla, I have different amounts here of things like silver and hydroxide, I need to do a limiting reactant analysis to figure out which one of these things, when completely consumed, will give me the least amount of our interesting silver hydroxide precipitate. So let's get into it. Let's see here. In my pantry, I had 7.04 times 10 to the negative 3 moles of silver ion, and I had 0.0385 moles of hydroxide. And now again, our intuition is probably tingling because We are in a 1-to-1 ratio here, right? Everything is 2 to 2. So since all species that are reacting and being formed are doing so in a 1-to-1-to-1 or 2-to-2-to-2, if you want to be specific, simplified ratio, then we would predict that if all of our silver were to react, then we would make 7.04 times 10 to the negative 3 moles of our silver hydroxide. And if we were to look at our hydroxide, since we have a 1-to-1 ratio there, if all of our hydroxide was consumed, then that would make 0.0385 moles of our precipitate silver hydroxide, AgOH2. Nope, AgOH. So since our prediction tells us what our possible mole quantities are, we see that this is the most limited quantity of product, meaning that silver itself, the silver ion, is the limiting reactant. It is what is consumed first or what runs out first in the chemical reaction. So silver ion is our limiting reactant. Let's prove this now quantitatively. So I need my pantry and I need my ratio, my recipe. So 7.04 times 10 to the negative 3 moles of silver plus, and I know from my balanced chemical equation that for every 1 mole of silver plus reacted, there will make 1 mole, and you know what, I'm not going to use my reduce because I don't want to confuse you. For every 2 moles of silver reacted, I create 2 moles of silver hydroxide. So when I cancel, I'm realizing I am multiplying by 2 and then dividing by 2, which does effectively nothing. This gives me my 7.04 times 10 to the negative 3 moles of product. This definitely matches what we saw. And let's again prove it with our work. For the hydroxide reactant, so based on my recipe, if I were to take my pantry amount of 0.0385 moles of hydroxide, my recipe says that for every 2 moles of hydroxide reacted, I generate 2 moles of silver hydroxide product. So again, multiplying by 1 effectively, 0.0385 moles of AgOH. So the limited quantity that was made is going to be the one that is determined by the limiting reactant. So we know that this has to be the amount of product that's actually formed. It's the lesser amount. So since this is the result, that is the possible maximum, so let's call this the max result. since silver is the limiting reactant, it runs out first. Then we call this quantity the theoretical yield. Meaning, in theory, if everything goes perfectly in this reaction, and I do indeed use up all of my silver that I had available, then I should be able to make this minimized or limited amount of product. Whew. Let's see if we're done. Uh-oh, how much in grams? No, Professor Caslin, why? So notice, to get this into grams, I need to take my theoretical yield of silver hydroxide precipitate, 7.04 times 10 to the negative 3 moles of silver hydroxide. And I want to get that into grams, so I am going to either calculate or Google the molar mass of silver hydroxide. So when I do this calculation, I get that the molar mass of silver hydroxide is 124.88 grams per mole. So then this is a conversion between moles and mass, meaning I use molar mass. And let's make sure that we've got these units right. So remember, anytime you hear a per unit, it's always numerator unit. Per one of the denominator unit. So it's kind of the general case. And we can also remember the definition of molar mass. This tells us the number of grams. That's not what I wanted. Stop it. Stop it, Notability. You're being a butt. Okay, there we go. So the definition of molar mass says that there are, let's see here, in 1 mole of silver, or if I had 1 mole of silver present, silver hydroxide, then that should weigh 124.88 grams. So it's always the mass of 1 mole. So the 1 always goes with the mole. So this becomes 124.88 grams in the numerator. Moles and moles will cancel. And then let's see here. If I were to take my mole quantity, and I'm going to put it into a decimal, so that's 0.00704, and multiply that by my 124.88 grams per moles, I would get 0.879. I'm limited to 3 significant figures because I had only 3 significant figures in my volumes and in my molarities. And there was no rounding that I had to carry through here. At least my calculator did not show those digits, but make sure that you are mindful of that. And this is our grams of our silver hydroxide precipitate. So this is our theoretical yield expressed in grams. All right. That's a lot. I threw a lot at you in this problem, but it doesn't go away. So these ideas of concentration, these ideas of balancing and double displacement, these ideas of complete and net ionic equations, understanding what a mole ratio is from our balance coefficients, understanding the solubility rules, and now looking at how to do conversions to moles using things like molarity or molar mass. These are all important when we begin our stoichiometry. So I'm going to finish lecturing for today. I think this was enough for us. I will be posting a video for you to watch on titrations just because I do want you to see this before we get into lab. We can do some more titration examples once we get closer toward the due date of this lab report, but I want you to just have an idea of how a titration works and how that involves stoichiometry before we do our titration experiment tomorrow on the 11th. So I am done for today. I will see you all tomorrow. Have a lovely Monday, and thanks, folks.